Hello, so our team decided to make a wearable awareness system for the hearing impaired. So like the previous team that made a system for the vision impaired, this is for the hearing impaired. So our team consists of me, Ethan, Shreyas, Nathan, Jonathan, and Robert. And Robert, Jonathan, and I make up the hardware team, whereas Shreyas and Nathan make up the software team. So overall, our goals are to make it wrist mountable so that it's convenient and easy to wear around. It will have a vibration motor to notify whenever a signal, such as a siren or a specific code word that is input into the device, will be heard, and it will vibrate and output what that is to the text display. It will match the intensity of the vibration with the intensity of the sound, so that way if there's a loud siren, you will know that it's a loud siren and it's much closer than a farther sound. And it our goal is to make it reliable so that way it has a good percentage of success, otherwise it's not very useful. So over here we have our schematics, which we are using the Teensy 4.0 microcontroller. And over here we have our microphone and our motor driver. Over here we have our system hooked up so that way we can test our components. Right over here we've got our feedback from the microphone. And then I'll pass it over to Shreyas, who will explain the software side.
Yeah, so basically the objective of our system is to take an inputted sound from the background and identify it as some sort of important sound to be detected and notified to the user, and then eventually, well, not eventually, but right after, notify the user that sound through vibration and text. So basically, this system starts out by powering on, checking if all the components are together and operating properly on the board. And then it goes into the listening phase where the system is constantly listening for sounds that break the threshold that is determined by listening to the background and basically determining a threshold that can change depending on where the user is, per se, maybe a street or at home. There's going to be a difference in those threshold levels. So that's what the listening phase is for. And basically, if there's a sound above the threshold, it'll go into the algorithm and pass that sound to the algorithm, which then detects and labels if that sound is in a list of sirens and alarms that we have, or if that sound is the user's name or any other impulse sound. So it will either label it in the category of labeled noises that we've detected, or it'll just say it's a loud, undetectable noise, so that the user is still informed that there's a loud noise. After everything is detected, it's just outputted to the display and vibration. That's all we have for that.
Any questions?
Have you thought about any solution for adding directionality? Like you can essentially somehow inform the user about the direction where the sound's coming from?
Right. That's one of our stretch goals for next semester is to add directionality, possibly have we're going to have an array of microphones so that we can do the calculations depending on what direction it's coming from. And also we're taking into account the position of, say, the arm. If someone has their arm up, it's different whether or not from someone that has their arm down.
How are you going to count, how's this thing going to operate in a noisy environment where all the noises are above the threshold?
Basically, it will determine the threshold based on the current background. So say there is a noisy environment, it'll make the threshold pretty high to the point where an impact noise would maybe be like a 1 dB spike or something like that. So it'll be more sensitive if there's a higher threshold, basically.
Have you done any kind of analysis that says that a Teensy is sufficiently powerful to do that kind of filtering?
Yeah, the Teensy mentions it's got what kind of megahertz?
It's 600 megahertz.
600 megahertz processor, which we've determined is plenty as far as signal processing for specified sounds that we're looking for.
Okay, and when running at 600 megahertz all the time, will it meet your goal for battery life on something that's worn on a wrist?
For that, we were considering, since it wouldn't be continuously running, it would be sampled, and that sample rate could be spread out in a range of, say, once every second or two, because the person's environment that they're in most likely is not going to be changing in an instant.
The other question I have just related to your goals, you need to make them more objective when it says, wearable on the arm and wrist. You need to translate that into, a number of square inches,
Right.
weight.
Right.
And think about what your form factor is ultimately going to be, and translate that back to what the electronics need to look like.
Okay.
If you intend to actually go and do a PCB that's going to fit on there, if you're going to keep it as a prototype and it's going to be spread out, then that's changed. But you still need to think about that, and put that into your goals. Also, you need to define what reliable with proper feedback means. That's very, very vague and really measurable.
So as far as size, the picture we have here of our breadboard, that plug is a micro USB, so it seems it's pretty small as far as that, but I agree.
I mean, that's the prototype, but if you intend to do something else, then define what that something else is.
Okay.
As if you were putting it into a legal document so that someone can say, yes, you did what you said you were going to do.
Following up on goals, you said display on a screen. Where is the screen?
The screen is.
Is it on the wearable? Is it on the phone?
Yeah, it's on a wearable. It's not included in the schematic design because that was going to be the easiest part to hook up. The microphone being the most difficult. It would sit on top of all the other electronics.
But in the same way that your processor running at 600 megahertz and how much battery it's going to chew up on a wearable, screens are notorious for chewing up battery, especially
Yes.
on a wearable. So you may want to look into that as part of your system profiling.
Right.
Yeah, so the screen is actually, it's not going to be an LED display like, iPhones or anything like that. It's just going to be a text black and white display. So it should save a lot of power.
And it'll only be on when impulse, so with the backlight.
What analysis or research did you do to determine what's considered a key sound, what's useful?
So that's one of our biggest roadblocks right now is our detection algorithm. Since our device is not going to be internet connected or connected to any other device that can communicate outside of it, our initial plan was to do machine learning and have a machine learned system of the sounds that would be recognized. We were urged to not recreate the wheel and use a similar system that someone else has created possibly. And our research doing that has been limited, and we've reached out to a professor for assistance that has a big background in voice recognition and similar systems. That way that we plan to work with in next semester.
But to further answer your question, basically what we decided with was, the sirens, like police sirens, ambulance, fire truck, gunshot for impulses, things that'd be dangerous, like, a lady screaming or something like that. And then doorbells, knocks maybe, and then the most important would be the user's name.
Yeah, I was thinking that you would at least come with a conceptual list, and then there's some of those which you could say, yes, this works, and those that don't.
Yeah.
Have some metric for evaluating those.
Yeah, we were.
First of all, make sure you talk to people that are hearing impaired.
Yes.
The customers.
On your batteries, we need to look at how much energy the vibration generator is using, how often it's going to run, and go through those calculations. So I think battery time is going to be something to look at.